Hi, so today let's use one episode to talk about this supermodular function and supermodular game. Okay, so we're gonna skip the mathematical proofs for a lot of results, and we're gonna continue and put all of those results together and try to present those key ideas in one episode. Okay, so you can have a look on those proofs and try to show those proofs by yourself if you're interested in those things. Okay. So before we talk about this supermodular function and the game, so for that, let's continue on some definition we had last time on the lattice. Okay, so we say that a lattice is complete. Okay, so some lattice, okay, let's say on X, okay, so instead of using the binary relation, letter R, so let's use something more straightforward, such as the greater than or equal sign, okay, as this binary relation. So this lattice, okay, so lattice this, it is called complete, okay, if for all, let's say some subset of X. Okay, so there exists the sup of S and inf of S. Okay. Okay, so for example, so let's say if X is something from, let's say, from 0 to 5, okay, and this is in R1, so X and with this greater than equal sign is a complete lattice, okay, so it's simply one dimension and we can always compare that, and because it includes both boundaries, so we can find for all those all those points inside of this interval, we can always find the sup and inf of that. Okay. And for a counterexample, okay, if let's say X is from 0 to 5, but not including 5, this boundary on the right, okay, so let's say this is not a complete, okay, so not a complete lattice. And this is simply because the sup of this interval of this set X, that supremum is not inside of X. Okay, good. So, and that's something remaining from our previous episode. Okay, good. So today we're gonna try to talk about this modular function and the corresponding game. So before that, let's first introduce a very useful theorem, okay, called Nasser and Tarski theorem. Okay, and it has a restatement of this theorem, and sometimes we call that simply as the Tarski fixed point theorem. Okay, and that fixed point theorem, and you can know that this is pretty related to the game theory, right? And we use those fixed point theorems to show the existence of the Nash. Okay. All right. So okay. So let's write this down. Nasser Tarski theorem. Okay. So let this L, okay, and this less than or equal sign be a complete lattice. Okay. And we're gonna have a function, this f, So it's a function from L to itself be a monotonic function with respect to this birelation. Okay. Then we're gonna say that the set of all the fixed points of this F in this L, those fixed points, they form, so the set of those fixed points, it forms a complete lattice under this relation. Okay. And if you want to restate this as the pretty standard way of saying this fixed point theorem, okay, so let's rewrite this as Tarski fixed point theorem. Okay, essentially they are the same thing. Okay, it's just they're talking about something, the same thing in different aspects. Okay, so let's suppose some x greater than or equal sign is a complete lattice as before. Okay, and we define this f, okay, also the same as before. Okay, from x to itself is monotonic, or you can call it as non-decreasing, maybe, for simplicity, okay, function. Okay, so now, so this is pretty similar as the previous definition, right? So let's have some subset of x. Okay, let's call this x star. Be the set of the fixed point of this f under this relation, right? Okay, so this set x star, that's gonna be those x where this x equal is equal to fx. Okay, so this is the definition of the fixed point. Okay, so that has to be on the 45-degree line in R2, for example. Okay, so that'll be the statement. Okay, we have something else. So the first that we're gonna have is that this set of all those fixed points, this is not empty. Okay, it has something, at least one, right? And second, okay, so we let this x star, let's put a upper bar here. Okay, so let's define this to be the sup, okay, of some set where we put some x inside of this, where we have fx is bigger than this x. Okay, so this is still a birelation. Okay, and similarly we define this x lower bar star to be the inf of some set, but we're gonna reverse this direction. Okay, we're gonna put x which is bigger than fx. Okay, so those are two sets that we just defined, and then we have some results from this theorem is that x upper bar star x lower bar star, those are in x star. This is pretty straightforward, okay? And for any of those x star in the x star, okay, in the set, you're gonna have this upper bar star is bigger than x star, bigger than x lower bar star under this bound relation, okay? And lastly, we say that as we just said in the previous version of the definition of the theorem. So we're going to say that this x star, this relation is a complete lattice as well. Okay. Good. So let's try to have a little example in R2. Okay. So so this actually is R1, right? Because we're gonna have this this R2 just to indicate this F, right? So we're gonna have this X to be R1. Let's say X is from 0 to 1 for this closed set, and we put this X here, okay, and this is Fx. Okay, so, and we're gonna start from 0 to 1, and we will focus on the area between here, okay? So, and this is gonna be the 45-degree line where we have the fixed points, okay? So, for example, let's say, so this is exactly, for example, we're gonna have this function, okay? Let's say from, let's say starting from here. Okay, let's change the color of this. Okay, it goes from here, and maybe it, let's say it, and then we have this included, and maybe it jumps, okay, somewhere like this, and then it goes like this, okay? All right, so we can see that those fixed points that we could find in this picture are those points, right? So this is one fixed point, and this is the second, the third, and the last, okay? So, and we can see from this, from those results is that, of course, this is not empty, okay? We have 4, okay? And then for the second, we're gonna define this X star upper bar to be the sup of those some x's where we have this fx is bigger than x, okay? So whenever we have fx is bigger than that, so that has to be above the 45-degree line, right? So that means, so let's use maybe maybe green, okay? So let's use green to indicate this. So when we have this fx above x, that's gonna be this part, right? Including this, and this, including this, and those two. Okay, so that's the part of this x upper bar star. So, and we're gonna have this sup, okay? So, and we know that this is exactly that, right? So this would be the x upper bar star, right? So at this point, okay. So, and we can also find the inf, right? So let's change another card, maybe using, let's say, yellow, maybe. Okay. Yep. So the definition for x lower bar star, that's going to be below this 45-degree line, right? Okay, so that's going to be this, okay, this part, and this part, right? Okay, good. And the inf, that's going to be here, right? Okay, so, and we can verify the remaining. So we say that those two there inside of x star, of course, yeah, and then this is straightforward. And for any x star inside of x big X star, we have those two as those two. We have the x star inside of so between those x lower bar star and x upper bar star, right? And we can also verify this on the picture. Okay, good. So this is pretty easy to verify, but actually this theorem, it says more, right? And this is also true that we cannot see this directly from this picture, but this is also a very powerful result. Okay, good. So so we're gonna skip the proofs, okay, because we want to try to complete all those statements and the results to try to finish the modular game in one episode. Okay, so if you're interested in those things, you can find and search for those things and have a look, okay, by yourself. Good. So this is the definition. This is the theorem for the Tarski fixed point theorem, right? So next, okay, let's continue. So next, we're gonna introduce. Okay, we're gonna introduce the supermodular functions. Okay. Okay, so for the supermodular functions, okay, let's define. So it's also defined on a lattice. For a lattice, x and this binary relation greater than or equal sign. Okay, so this is just a binary relation. Okay, we don't define the meaning for now, so, but you know that this is a binary relation, and a function. Okay, f. Okay, so this will be a function from x to r. We're gonna call this f function f is supermodular if for all x and x prime in x we have, so this is a definition of the supermodular function, we have this f of x join x prime plus f of x meet x prime. So this should be greater than or equal to the sum of those two, fx and fx prime. Okay, so essentially you can imagine the meaning of this definition, right? So when we have the sum of the join and the meet of 2 points inside of x, and this gives a weakly higher value than the sum of those two by themselves. Okay, so basically we for example, if you can imagine that on a so x1 x prime there on r2, okay, and we're gonna have some supermodular function. So that when we have this kind of the join, okay, so for the soup of this lattice, we're gonna have a pretty high value on the third dimension, right? Or on the dimension of this f, where it maps to some other real number, right? But it's not that high, or it doesn't have pretty high value for those points with fx and fx prime, right? So that would be essentially what this is talking about. Okay, so and for example, okay, so let's say example that we just mentioned. So x, that could be R2, okay, and we have this f, okay, for x for the first and second dimension, R2, and let's simply multiply them together, okay. So this is gonna be supermodular, okay. And it turns out that a lot of functions they're supermodular, right? As long as they satisfy this requirement. Okay, and you can verify this by yourself, right? Basically, so you can just consider 2 points on R2, and then you can verify that this inequality it will hold, okay, by this function, and there's nothing difficult here. Okay, good. So and yeah, so if you have 2 points, okay, and you can discuss that if, let's say, if you can compare those 2 points directly, or you cannot compare them. Okay, if you cannot compare them directly, then you might need to find their join and meets, which are not those 2 points themselves, right? But in the other case, although you need to find those points, but it's still not straightforward. It's still pretty straightforward, right? Not very difficult. Okay, then you can just rearrange the terms and verify this inequality. Okay, good. So we just skip that for now. Okay, good. So let's continue our discussion next. So we say that so now we have the supermodular definition of supermodular function. Okay, so next we're gonna define the strict supermodularity, and also we're gonna define the submodularity. Okay, so for a lattice x and this, so a function f from x to r is strictly supermodular if for all points x prime in x we have neither x is bigger than x prime or x prime bigger than x, so we cannot directly compare them. And then we have this the join plus the meet is strictly bigger than the sum. Okay, this is also a very natural definition, right, based on the supermodularity. Okay, and we can also say something about submodularity. So f is strictly submodular if minus f is strictly supermodular. Okay, so you can just reverse all of those inequality and get this definition for the submodularity. Okay, good. And we're going to have something also very useful when we study the supermodular game. So that's going to be called increasing difference. Okay, increasing difference. So basically, this is talking about the strategic complementarity, okay, or just complementarity, okay. Basically, this is important in economics, right? So the definition is that for partially ordered sets, for PO sets, X, okay, and the by relation in some set Y. Okay, so a function f from the cross of x and y to R1, it has this increasing difference, this feature, if for, okay, let's say for 2 points in x, okay, x prime and x double prime in x, y prime and y double prime in y. So we're gonna say that this x double prime is bigger, okay, and y double prime is bigger. Okay, so what we're having is that the f of x double prime and y double prime with those bigger ones, okay, minus y is bigger, y is smaller, and this has to be bigger than or equal to y is bigger, y is smaller, minus the f, both smaller, okay? And you can rearrange this. So this is essentially talking about something else, that the same thing essentially, but we can rearrange that both two bigger plus both of two smaller, and this is bigger than greater than or equal to the sum of those mixed ones. Okay. All right. And then from here, this is very this looks very familiar, right? So this is pretty similar to the supermodularity, the supermodular function. Okay. All right. Good. So before we can talk about the supermodular game, so we still need to talk something else. Okay. So and now we have defined the supermodular function. Okay. So we're going to ask that how do we optimize them, right? Optimizing supermodular functions. Okay. So again, we let x and this be a lattice. Okay. So what we can talk about the optimization properties, or the some properties when we try to optimize the supermodular functions. So we can say something here. So if function f from x to R1, if that is supermodular, okay, then the argmax of that, so this has to be x, okay, so that is a sublattice of x. Okay, this is pretty useful for later. And second, if this function f again, if that is strictly supermodular, then the argmax of fx, okay, by choosing some x, that's going to be a chain, as we discussed before. Okay. So on a chain, we can always compare those elements inside of this chain set, right? So we don't bother to write this definition again for the chain. Okay. So, and again, we're going to skip the proofs. Okay. So, and something else. So the reason that we skip all of those proofs is that we try to squeeze those useful results together to help us to quickly and better understand those things coherently, right? Okay, so let's see. So we say that, so that this x and the binary relation and y, so we're gonna have two lattices, okay? B2 lattices. Let's suppose this, let's have some supermodular function, okay, the cross of xy to some R1. So this is supermodular. Okay. So let's suppose some function v of y, and that is the supremum of xy that is finite for all the y's. Okay, then we can say something about this v. So this v has to be supermodular as well. Okay, and this is very useful for later for our proof in the supermodular game. Okay, good. So, and now we're almost ready. So something else we're gonna also need is a compact lattice. Okay. So we say that, okay, so if some x in Rn that is compact and non-empty, and we have this lattice, then there exists some x upper bar and lower bar, okay, such that for any x, we're gonna have xx lower bar. Okay, let's use the boundary relation. Okay, x upper bar bigger than x lower bar. Okay, and this is a lattice that is also compact. Okay, and this is a very natural definition as well. Okay, good. So next we can talk about the monotone comparative statics. Okay. Okay, so let's suppose some x in Rn is compact. Okay, also we suppose this x with this sign, the binary relation is a lattice. Okay, so this partial order is lattice. And then we say we're gonna also assume some y. Okay, is a PO set, partial order set. Okay, and we can also say that f, this function, it has some requirements. Okay, so the cross from x and y map to R1 satisfy the following requirements. So the first is that for each y, this f, okay, xy is continuous. Okay. So this x can be anything. Okay. And for each y, this again, this thing is supermodular. And lastly, this f has the increasing difference. Okay. And then we can say that for each y, the argmax f of x and y, this has a greatest and a least element. Okay, denoted as x upper bar y and x lower bar y. Okay. Then also for y and y prime in y, so if y is bigger than y prime, then the greatest one with this y is bigger than the greatest one with y prime, and also true for the least one. Okay. All right, and this is also something related to the complementarity, right? And this is also a very useful comparative statics, as you can see from this from the comparisons of those results, right? So when we're having a bigger y, okay, so we have both of the greatest element and the least element bigger than the other one with the smaller y, okay, and this is also very useful comparative statics on lattice, right? Good. So okay, so finally we can get to the supermodular game. Okay, so in supermodular game, that would be a very useful application from this from this monotone comparative statics, okay, defined on this lattice. Okay, so that's gonna be the last topic that we can talk about for today, supermodular game. Okay, so let's define this game. So this supermodular game, that is essentially just a simultaneously move game. Okay. Okay, so let's say we have the set of players, okay, from 1 to, okay, up to the cardinality of I. So the set of I players. Okay. And let's say the strategies, okay, we have a set of strategies, okay, SI. This is for each player I, right? This is not the profile. We have strategy for each player. So there's going to be a subset of R and I, okay. All right. And so that is defined as some compact set of strategies of player I. Okay. With respect to this partial order. Okay. So, and about the utilities, UI, so that's gonna be the cross of each player in I, okay, and from the SI map to R1, okay. This is just utility function. So this is gonna be the payoff for player I. Okay, so we're gonna also assume that some continuity, right? So U I S I S minus I. We're gonna say that this is continuous in SI for each I minus I, and also the same continues in S minus I for each SI. Okay. All right, and then let's call this simultaneous move game. By, let's say, some G. Okay. So this G is a supermodular game. Okay. Let's define this. If for each player I have first, we have this strategy defined on the lattice, right? So we're gonna have this strategy set of strategies as with some parameterization that is a complete lattice. Okay. Second, the utility function, okay, is supermodular. And lastly, the utility has the property of increasing differences. Okay. In the Si and S minus I. Okay. All right. So, and we can talk about the some best correspondence, right? So the best correspondence of player I. Okay, that's gonna be, let's use this BI as notation for the best correspondence. Given strategy from minus I. So that's gonna be the set of SI where the utility for player I is weakly higher than some deviations. Okay, for all SF prime. Okay. So G has, let's say, this is called monotone best responses. Okay. So if for all I first for all S minus I, this BISI has a greatest element. Let's use this BI upper bar. And a least element, BI lower bar. Okay. And second, the BI upper bar as minus I, and the lower bar S minus I are non-decreasing in S minus I. Okay. All right. And next, we're going to have some key claims. Okay. So those are the definitions, right? And those are pretty similar to the definitions of the monotone comparative statics, right? So then we're gonna show those results, and those are pretty similar to the previous ones, right? So I'm gonna say that a supermodular game G has monotone best responses. Okay, and this is simply just exactly the same as what we were talking about the monotone comparative statics, right? And the proof will strictly follow for that. And another important claim, and also the most important one for this episode, is that if a supermodular game G has monotone best responses, okay, then we can claim that this G has a pure strategy Nash equilibrium. Okay, so and now we're gonna use the Tarski's fixed point theorem, right? So essentially, the proof of this claim. So first, we can you can define the greatest element, right? And for this best response, and then you can show that this is a non-decreasing function from some complete lattice to itself, right? And then we can use the fixed point, the Tarski's fixed point theorem, and then that would be naturally giving us this pure strategy Nash equilibrium, right? Since we have defined those as this within the requirements, right, of this fixed point theorem. Okay, so then up to here we have shown a lot of interesting results, and basically those results are based on the lattice, and then we use those things to show the very useful application on the supermodular game based on the such as the monotone best responses or the monotone comparative statics, right? Okay, so that'll be basically for this episode. Good.